Hello everyone, today we're going to look at a rather simple algorithm called the Egyptian or Russian multiplication algorithm. It's quite simple and intuitive. Let's have a look at it. So for example, say we have a problem. We need to do the product of two numbers, 16 and 35. For the math Olympiad people, you guys will be able to quickly decipher its value, but for the slow ones like myself, it will be quite difficult too. So what the ancient Egyptians did was they leveraged the principle of doubling and halving. Yeah. So what happens is, 16 times 35 is the same as 16 times 35 times 1. And 1 is the same as 2 over 2. So we can halve the 16 and then we can multiply the 35 by 2. So when we halve the 16 and multiply 35 by 2, we end up with 8 times 70. We continue on the same procedure. We halve 8, we multiply 70 by 2. We have 4 times 140. We have 2 times 280. And then we have 1 times 560. And so at this point, we know that the solution is actually 560. What of the next example? Say 9 times 7. In this case, we see that 9 divided by 2 and then 7 times 2. 7 times 2 is 14, but 9 divided by 2 is 4. And this result is not the same as this result. Okay, so how do we go about it then in this case? Because in the previous case, 16 is a power of 2, and so it was very clean when you did the division. And so let's look at how the ancient Egyptians went about solving this particular problem. So say we want to compute 9 times 7. We write 9 under the A and then 7 under the B, and then we have an accumulator, which is R. Essentially, it's called, I call it a result, and then we initialize it by 0. Okay, so B, we look at B. B is odd. So when B is odd, we add the values of A and R. So 9 plus 0 is 9. So it goes to the next stage. Then we multiply A by 2, we divide B by 2. Essentially the same principle of doubling and halving. We multiply 9 by 2, we have 18. We divide 7 by 2, we have 3. We do the integer division. Essentially it's supposed to be 3.5, but we are doing an integer division. And then we continue on the same process. So to move on to the next place, we have 3. 3, is it even or odd? It's odd. So we add the values of A and R, then we have 27, and then we multiply A by 2, we divide B by 2. So we have 1, we have 36, we have 27, okay? To move on to the next stage, we say, is 1 even or odd? 1 is odd, so we add 36 and 27, then we have 63, and then we multiply A by 2, and then we divide B by 2. We end up with 0, and then this is the stopping criteria. So essentially the algorithm is as follows. So we initialize R with 0, and while B is greater than 0, if B is odd, which is essentially this line, B mod 2 is equal to 1, then we add R to A, or A to R, and then we multiply A by 2, and then we divide B by 2, and then we return the value for R. But what of the modular variant? Can we tweak it a little for the modular variant? Yes. So it's the same procedure. We have A to be 27, B to be 13, and R to be 0. B is odd, so we have 27 plus 0 to be under the R. And we multiply A by 2, we divide B by 2. We divide B by 2, we have 6. We multiply 27 by 2. That's 4, 14, 54. But we are working in a modular range, so 54 mod 37 is 17, so we end up with 17 here. Then we move on to the next stage again. So it's the same procedure, but this time around we see that 6 is even, so we maintain our R. Then we multiply 17 by 2, which is 34. It's less than 37. And then we divide 6 by 2, we have 3. Then we continue on again. So 3 is odd. So we add 34 to 27, we have 61. 61 mod 37 is 24. So we have 24 here. And then we multiply this by 2, 34 by 2. So 34 by 2 is 68. 68 modulo 37 is 31. And 3 divided by 2 is 1. And then we proceed. So we have 18 here. We have 18 here because 31 plus 24 is 55. And 55 modulo 37, we're working on modulo 37, so 55 modulo 37 is 18. Multiply this by 2, we have 62 modulo 37 is 25, and then we divide it by 2 is 0, so this is our stopping criteria. So the algorithm follows the same thing, except this time around we have our modulo operation down here, and then also we let capital A represent the residue class, or the residue for A mod n, just in case A is greater than or equal to n. Okay, so essentially the algorithm follows the same procedure. But then also there's something called the Newman's algorithm in solving mode. I would add it to the description, the paper in which I found it. Suppose we have, say, C is congruent to AB mod M, and let C represent, say, A times B, okay? So let's say, for example, let me use an example to explain. So we have 621 mod 7, and we need to find the remainder, yeah? So we write 621 minus R is equal to 7 D naught. Essentially, what we're going to do here is we're going to multiply the 7 by 2. We have 14, 14 by 2, we have 28, 28 by 2, 56, and so on, up to 448. Why do we stop here? Because the next value is going to be greater than 621. Okay, so there's a stopping criteria. Then what do we do next? Because 448 is lesser than 621, we say D6 is equal to 1. And then when this is equal to 1, we can subtract 448 on both sides, or essentially, as some people say it, we move 448 to the left-hand side and subtract from 621. Then we end up with 173. Okay, then we have 173 minus R is equal to all of this relation up to 224 D5. And because 224 over here is greater than 173, we say D5 is equal to 0. When D5 is 0, this goes out, and then our relation maintains, and then we have 173 minus R, 7 D naught plus this up to this on the next line, so D4. And because 112 is lesser than 173, we do D4 is equal to 1, then we subtract, and so on and so forth until we get to our final solution, which is 5 minus R is equal to 0. So essentially our remainder is equal to 5. And so we can simply look at the correctness. This I wouldn't explain much because I wanted it to be simple, but this for those mathematically inclined. So essentially, for the correctness, we also look at the termination, and in the algorithm we see that B always is being divided by 2, and so at some point it's going to reach 0, and in that the loop will terminate. Okay, and for the correctness, this correctness essentially is talking about the loop invariance. All right, so I wouldn't talk much about this one, and I want us to move on to the implementation of the Egyptian multiplication algorithm, without the modulo in Nasm. I find that quite interesting. All right, so let's try to implement it. Okay, so I'm going to create a new Nasm file, which looks like this. Okay, so in Nasm, I'm going to include my macros.inc. This particular document you can find in the description below. Okay, it's actually in my GitHub. I'll add it to my description below. And we also have, I'm going to need atwa, which is a function for converting a string to int. Convert C function to convert, string to int. And then for every Nasm file, we're going to have 3 sections. We have the data, we have the .bss, and then we're going to have the text, which essentially begins the code, which shows where the code begins from. And for the .bss, essentially here we keep in the uninitialized variables. So here I'm saying that I'm reserving 20 bytes, okay? And over here I'm going to need a few things here. So I say new line db equals 10. This is essentially the ASCII character for new line. Oh, by the way, we use the semicolon for comments. Then we're also going to look, I'm going to need some things here. Let me write it this way, db arrow to command line arguments needed 0 and 10. And I'm saying its length equal u, and I'm saying the command line error. Okay, I'll get to the explanation of these 2 lines. So once we have this, we can begin the directive. Always begin with a start, okay, underscore start. So here I say RSP. RSP over here is going to contain the number of command line arguments, and I'm saying that move that variable into R8. What I mean by command line argument is at the end, if we want to run this program, we're going to have it this way: Egyptian and say 9 and 7, okay? And so we have 1, 2, and then 3, okay? So RSP is going to contain 3. We're going to check whether RSP contains 3. And then if it's 3, we're going to have to convert these variables, numbers, 9 and 7, characters, 9 and 7 to integers. Otherwise, we have to exit our program. This is quite similar in C, for those used to C. So we say the RSP contains the number of command line arguments, okay? And we're going to say, we are going to compare it to the value of 3. So we are checking whether it's 3. And if it is 3, we say we're going to move to a new label or directive. Otherwise, we're going to say print command line error, and then the command line error length, okay? Essentially, what it's going to do is, and then also we're going to exit 1. The exit value is going to be 1. This print and then exits already macros defined in the include my macros. So you just have to look at the description below and then you'd find them. It makes the code look simpler and cleaner. And also what I wanted to say is, so it checks whether there are 3 variables or 3 arguments in here. That's including the program name, the first variable, and the first number, and then the second number. So if it's not 3, it's going to print out error 2 command line arguments needed. And then this particular line over here essentially does counts the number of bytes, the number of bytes in here. And so command line error length essentially counts the number of bytes in here. This operation helps us count it, and then this is just a string, okay? So there is nothing weird going on here. Okay, and so if it's actually 3, we're going to have to move on to the convert int, okay? And so we're going to create a new directive, which is the convert int. What we're going to do here is going to write this RSP plus 16. And so this gets move essentially move the first command line argument into RDI. Okay, so listen, because integers 9 is represented as 8 bytes, so we're going to have 16. If we had written 8 over here, it's going to reference the Egyptian instead. So we have, sorry, not about integers, but we have like 8 here to represent the first command line argument. The second command line argument is 16. The next one you think was going to be is going to be 24 because it has a difference of 8. So the next one is going to be RDI RSP plus 24. It's going to have a difference of 8. So that's going to be move the second command line argument into RDI. Okay. Now after moving them, we have to call the atua function, which is essentially, I wrote up here, is a C external C function to convert string to int. So we call atua, and it's, well, when atua converts the value, it's going to place it into RAX. So I'm just saying that move the value, the result of the atua, which is essentially the value, move the value into R12. So we do the same thing for this one. So we call atua again, and we say move the result in, atua always places the result in RAX, so move it into R9. Okay, and I typically like it this way. Let's move the R12 back into R8. Okay, why? Because this is the B value and this is the A value. Okay, and we're going to sort out R12, which is the result. We're going to use it the result, which is R. Okay, all right. So I hope we're clear about this. So now R9 is going to contain our B value, R8 is going to contain A value, and then zeroing out R12 essentially makes R12 be equal to 0. Okay. So after doing that, what's the first thing that we do? We check whether the value is odd or even. And what do we check? We check whether R9, which is the B value, is odd or even. So we have a simple command or operand over here, which is a test R9 against 1. And then we have a new directive. So if it is odd, then we are saying that add R12 to R8. Essentially what we usually do. So we're saying the result, we are adding A to the results, okay, and then keeping it back into our result. Okay, it's nothing new over here. Otherwise, we jump to a directive I'm going to call Egyptian. We haven't written it yet. Okay, and in the case where it's even, it does nothing. It also goes back to the Egyptian. Don't worry, we'll look at all of these. Okay, so we have the Egyptian here. And remember, after that, what do? We halve the B and then we multiply A by 2. Okay, and we have the simple operand, which is the shift left command. So shift left 1, and this is the multiplication by 2, and then shift R, which is, this is the division by 2, and then I'm going to say jump to something called the check condition. Okay, so we create a new directive or label, which is a check condition, and then I'm going to say if R9 is equal to 0, like the condition on the while loop, and then if it's equal to 0, we're going to go to a new directive called done. Otherwise, we're going to jump back to check odd and even, and then the process begins again. So it jumps back to this, and then we test whether it's even, it's odd, and then we continue on the process and so on and so forth. Okay, and it's even. So now we're going to write that it's even directive. And so in the case where it's even, we're just going to go back to Egyptian because there's nothing to do here. And then we also need to write the done. So in the case where the value is done, we're going to print the number and place it into our reserved bytes, which is the output. It's defined up here above. Here, output. Okay. And the print num also is a macro in the. It's a macro in this. Okay. So we print the number. Then of course we want to make a line, so we have to print a new line. And then we exit gracefully. Okay. So let's save this and let's run this. I already have a script, say a shell script, and then we run this command. Okay, no errors, and then we say Egyptian 5 and 3. 5 times 3 is 15, so it should give us 15. Okay, let's do the 9 and 7, which is 63. 63, and let's do 7, 7, 49. Whoosh. If that had given me a wrong answer, I would have gone crazy. Okay, so yeah, and also we have to do the Newman's one, but this time around I'll do it in C. So okay, we're going to have the macro. I'm using the macro text editor because, well, I like the macro text editor. So we include, of course, our standard IO, and then we also include standard lib.h, you know, the usual. And we're going to say int main, int argc, and the char argv, and we're going to return 0. And then we check whether our command line arguments are sufficient. So the same thing, we're going to need 3 values. Wait, did we need 3 values? Yes, we're going to need 3 values, including the program name. I don't like it this way. So let me make it count, and then define it up above here. Say count 3. Yeah, now this looks beautiful, doesn't it? And we're going to print, in the case it's not equal to 3, we're going to print the standard error, the usage %SCM, where the M is the modulus, and yeah, we say argv0. This prints the program name, and then we have exit failure. Okay, and we're going to have to convert each to an integer using the atwa. And also we're going to convert to an integer, and we're going to have to print our result. Okay, %d like this, Egyptian mod, and then we're going to pass in the addresses for C and M to do the computation for us. Oh, and of course we're going to have to write the function. So the function is going to return an int, so we say Egyptian mod, we pass in the pointer and M, okay, and we're going to have to do the loop. So we have the while loop, M is less than C, then we're going to say M is equal to M times 2. No, let me do it this way. This way, yeah. That's the same thing as the same thing as M equals M times 2. But I like the shifting, you know, the bit shifting, the shifts left, okay? This operation is a bit shift left, which is essentially multiplication by 2. And I'm going to need a new variable called count. And I'm going to write int count so we know the count where we are when we are doing the multiplication and how many differences we should take. And then we have the count. Well, count is greater than 0. if m is less than c, then we say c equals c minus m. Okay, but I like it this way. Yeah, it makes me look like a serious programmer, but I'm nothing of the sort. And then we're going to divide m by 2, which is the shift right, divide by 2, which is, yeah. And then we have the counts. We're going to reduce the count, and then we return our c value. Okay, so let me save it. Everything has been aligned properly. Oh, I don't like you here. You should go up there somewhere. Yeah, you should go up here. You belong here. Okay, so let's compile this. Oh, it's already here. Yeah, I've already done it. Okay, so when I try to compile this, I like to add, the flags, which is the G, war, extra, and all that. So I know I can use it for debugging and all that. So yeah, no errors. So I say Newman in our 621 mod 7, and this should give us 5. Fingers crossed. So the result is 5. So this is essentially what I wanted to show you guys, and I hope you guys would come back to the channel, and next week we're going to talk about the methane reduction algorithm. It's also quite simple in its structure. So yeah, that's it. That's all from me, and I hope you guys have a blessed week.